Chapter 25, Comparing Counts. Now we're going to shift our attention away from quantitative data and into categorical data, things we can count. So now we need to test hypothesis for categorical variables. To do this, we will be using one of three methods. So within this chapter, we have three different types of tests we'll be doing. So you see it's going to break down each day. We're going to do a different test. First is the goodness of fit. Compare the observed distribution of a single categorical variable to one expected distribution based on a theory or a model. Then we have the chi-square test for the homogeneity. Compare the observed distribution in several groups for a single categorical variable. And then the test for independence. Examine the observed counts from a single group of evidence of an association between two categorical variables. So tomorrow we'll look at the goodness of fit, the next day, and then the next day. Now, within these, we need to check for certain conditions. We have a new condition, the counted data condition. Data observed must be countable. So we're not going to use anything that's proportions or percentages or measurements. Counting variables. Independence assumption. Randomization makes the independence more plausible. So we need to make sure that everything's randomized. The 10% condition. Sample is less than 10% of the population. And then the expected cell frequency condition. We should expect at least 5 observations or individuals in each cell. Now notice what's missing is the success failure condition, but that's kind of what's going on here, more or less. Remember the NP is greater than or equal to 10? We need to make sure our cells are greater than or equal to 5. We have a term that changes a little bit. Same term, degrees of freedom, but now it equals to the number of cells minus 1. Now notice I mentioned cells twice. What in the world is a cell? A cell is one element of a table corresponding to a specific row and a specific column. So, we have a column, we have a row. That would be one cell right there. So for each of these, notice this is, each of these I need to make sure I have more than 5. So this will be a nice cell, right? I have more than 5 here for this column and this row. I have more than 5 here, more than 5 here. This barely passes, I need to make sure I get more here. So I may need to run some more samples. This may not pass the condition for the, move on, expected cell frequency. So all of these pass except for the 3. That needs to be greater than 5 in order to pass that condition. Now note, how many total do you see? 1, 2. So my degree of freedom would be what?
2.
Equal to the number of cells minus 1. So what's my degree of freedom for this table? 1. Yeah. Number of cells, so I have 2 and 2, 1. Within this chapter, we are going to do what's called the chi-square statistics, used to test whether the observed counts in a frequency distribution or a contingency table match the counts we would expect according to some model. Note our notation is, you see an X, but this is the Greek letter chi, so it's a slanted X or a fancy X squared. And that equals the sum of all of our cells with the observed minus expected squared over the expected. And we'll demonstrate this more tomorrow. And again, of course, there's a calculator method too. As far as the chi model, notice it's not really the normal model, is it? So we're shying away from the normal model when we're dealing with categorical data, and we're going to look more as a chi model. Notice there's no really standard model. I have something going on here, and it changes based on my degrees of freedom. Likewise, notice how as you increase degrees of freedom, how it kind of changes the model a little bit. So So we'll look more on the chi model tomorrow. But note, it's not based on our model. It's based on its own type of model. And it does change based on your degree of freedom. Now we're going to take this data from tables. A two-way table is where each cell of a two-way table shows counts of individuals. One way classifies a sample according to a categorical variable. The other way can classify different groups of individuals according to the same variable, or a different categorical variable within the same individuals. Meaning, I have children, teens, and adults. This is categorical, right? Are you a child, are you a teen, or an adult? Compared to what they like, chocolate, vanilla, either. So I'm taking counts. You, what do you like, chocolate or vanilla, or neither? You would tell me something and I'll mark it. And then just keep on marking as I go through, and then count them up. That will create my two-way table. Now a more specific type of two-way table is a contingency table. It classifies individuals according to two categorical variables. Probably used more common is between male and female. So that would be a contingency table. You're just comparing two things. And note that these two things are categorical. They're countable. Like, you don't see any like 40% here, do you? Or you don't see males score 15 points a game of basketball. Countable. Now, if we choose to reject a t-squared test, so we have those three different types of tests we're going to do, and if we reject the hypothesis, an examination of the standardized residuals can sometimes reveal more about how the data deviated from the null model. Here's the formula. We'll look at that closely. What that basically is saying is, I run a test. See, I had a 1 degree of freedom. How does it deviate from other degrees of freedom? Let's say if I were here at 5. What is my deviation from this green to the other ones? More so the margin of error, as we said with quantitative data. So this is a big chapter. We have lots of new terms. We're dealing with a completely different type of set of data. And we have 3 different types of tests.